All right. Device connected. How many people do we have? All right, we'll wait 1 or 2 more minutes, see who else we get. All right, let's get started. So first of all, has anybody started on Tuesday's project? So if anybody does anybody who started on Tuesday's project have any questions about using the software? Okay, well, when we left off last time, we had been going over the rules for thin films. And there are 2 rules that I'm going to try to explain the origins of. One of them is that if your wave is reflecting off of something with a higher index, then that reflectance is flipped. Right? And if it's reflecting off of something with a lower index, it's not flipped. So if we're going from air to water, the wave comes in like this, the wave that's reflected off the surface will look like that. Whereas if we were going from glass to water, and the wave that was hitting the surface looked like that, the wave that's reflected would also look like that. The other thing we found was that if we played with these, let's say that N3 is bigger than N2, we got that the reflected field equals 0 if N2 is the square root of N1, N3. Now, I should be careful about what we mean by reflected field, because there's the reflectance at a single interface, and then there's the sum of just this reflectance plus that reflectance, which goes there, makes a round trip, comes through, and the wave that makes a second round trip, and a wave that makes a third round trip. And it's the sum of all those reflectances that we actually detect. If I'm standing somewhere over here trying to detect light, I can't say, oh, I only want the wave reflected off of the first surface, or I only want this reflectance that made one round trip, or I only want the one that made two round trips, or I want this one and this one, but not the others. I only get to choose some of them. I only get everything. I don't get to choose some of them. We want to try to understand that as well. Any questions on the big ideas from last time before we go into the origins of these things? Okay. So it all comes from solving the wave equation. Let's set up a coordinate system. And we're going to say that the interface between these two media is at x equals 0. So I'll have my y-axis, my x-axis, and my z-axis coming out of the page. And we'll just consider the very simple case of an electric field polarized in the z direction, hitting the surface at normal instance. So what we're looking at here is the z component. I know I've drawn it vertical, which you would say is the y, but I can't really draw it coming out of the page very well. I guess I could try, but so we're just going to leave that alone. And this has to obey the wave equation, which is that partial squared Ez by partial x squared plus partial squared Ez by partial y squared plus partial squared Ez by partial z squared equals partial squared, well, 1 over c squared partial squared Ez by partial t squared. And we normally write plane waves. How do we normally write plane waves? Remember from a few weeks ago, if you can.
With the dot product of k and r on the exponential.
So Ez should be some sort of amplitude, e to the I, kx times x plus ky times y plus kz times z minus omega t. That's if we have a wave. Well, that's for any wave. Now, if this thing is going to the right and it's hitting at normal incidence, what are the values of ky and kz? Don't overthink it.
Zero?
Yep, because it's going straight to the right. Okay. So Ez is just a e to the I. I'm just going to write k rather than keep putting in the subscript kx minus omega t. Except I should probably be a little bit more careful. What's the value of k in a medium? Is it just k naught that's value in vacuum, or is it k naught multiplied by something?
We have to account for the index.
Yep, so I can rewrite this on the left side as a e to the I n1 k naught x minus omega t. Now, let's see here. That's not the entire wave. That's just the incident wave. That's the wave that's traveling to the right. The reflected wave well, that's going to be Ez equals, I'll explain why I'm putting this thing here in a minute. I'm calling this R12 because it's a reflection coefficient for a wave starting in medium 1 and reflecting off of medium 2. And you're thinking, why am I writing R1 to A instead of, I don't know, just something called B. I mean, I could, but I just want to emphasize that the reflected wave is, the strength of the reflected wave is proportional to the strength of the incoming wave. If I send in a really bright light beam, whatever's reflected, it won't be as bright as that, but still it'll be pretty bright. If I send in a really faint light beam, whatever is reflected will be even fainter still. So the reflected wave is proportional to the incident wave, and this reflection coefficient reflects that fact. No pun intended. Also, why is it minus N1 K naught X instead of plus N1 K naught X like I have there? Well, what direction is the reflected vector?
It's because it's being reflected, so it's negative X.
Yeah, it's going to the left. The X component of the K vector is negative because the K vector points to the left. Now, there is another wave. Some of the light gets transmitted. And by the way, you see this all the time if you just simply look at a pane of glass. If you look at a pane of glass, if you look at a window, you see your own reflection. It's not, in the daylight, it's not as bright as the light coming from outside on the other side of the window, but still you see some light reflected off of the window, and you also see some light transmitted through the window. So we've got this wave that's reflected, and I'm going to say that, sorry, this transmitted wave. For that, EZ equals T12 A e to the I N2 K naught X minus omega T, where the N2 is due to the fact that now it's in a different medium. And again, this T12 is a transmission coefficient. And it just is, it's just consistent with the fact that the transmitted light depends on the incident light. If the incident light is bright, the transmitted light will also be pretty bright. And if the incident light is faint, the transmitted light will also be pretty faint. Okay, so I can write all these down. I can give names to things, but I haven't really calculated anything. I've just said I'm going to give things names. These things have to obey the wave equation. And the wave equation has a bunch of second derivatives in there. And physics majors like to think, I certainly like to think of my freshman calculus class as half pointless. Look, all I need to know is, how do I take these derivatives? How do I do these integrals? That's what I want to know. I need to know how to actually do these integrals. Why is this professor blabbering on about continuity conditions and epsilons and deltas and the necessity of continuity in order to evaluate a derivative? Well, you know, we've got some different physics going on the left and right side. On the left side, we have a wave going to the right and the left. And on the right side, we just have a wave going to the right. I've got three different expressions here. And at this interface, if I plug in X equals 0, well, let's back up. If I told you X equals minus 33, you know I'm on the left side. You know that the refractive index is N1, and I should use a combination of these two expressions to calculate the field. And if I told you that X equals plus 158, you'd be like, oh, I'll use that one. What if I tell you X equals 0? Which medium am I in?
Sorry, could you repeat that?
If I say to you X equals 0, which medium am I in, and which expression should I be using to calculate the field? Yeah, it's ambiguous. There's no obvious answer to this question. We could really use either of them. Physically, either of them would be valid, which means that we'd better be able to use both expressions. Those two expressions had better give the same result. That's the physicist's way of saying what the math professors were blabbering on about when they said that it needs to be continuous. So
Oh,
if I plug
um,
in X, did somebody have a question?
Sorry, is this the same as like establishing boundary conditions?
This is exactly a boundary value problem, yes.
Okay.
So X equals 0, E on the left-hand side is just equal to A e to the minus I omega t plus R12 e to the minus I omega t, because you know the kx and the n1 k naught x and minus n1 k naught x are both 0. If I use the right expression, t12 a e to the minus I omega t. And these two things had better be equal to each other. Oh, and there should be an a over here. So a e to the minus I omega t plus a r12 e to the minus I omega t equals a t12 e to the minus I omega t. E to the minus I omega t cancels out because it tweeted something terrible. So does a, so they are both canceled. And I'm left with 1 plus R12 equals T12. Any questions? We still don't know what R12 and T12 are. We just know that whatever they are, they satisfy this condition. Now, this equation up here has second derivatives. And we should be able to take a second derivative. If we want to take a second derivative with respect to x, well, a second derivative is a first derivative of a first derivative. And we can't take a derivative of a discontinuous function. That's one of the things that math professors beat into our heads as freshman physics majors. And generally, we ignored that either because we were so lost we weren't getting any of it, or because we were getting all the stuff that involves calculations and figured, yeah, we're physics majors, we're too cool to worry about all of this tedious rigor and proof and epsilon and delta stuff. Except then it turns out that we need it. Several years ago for a research project, I had to relearn a bunch of stuff about concave and convex functions so that I could do variational calculus with second derivatives, not just first derivatives. And if you're thinking, I don't know what the hell any of that means, why would I care about it? That was exactly my thought as an undergrad too. And then I had to use it in a project. So try to listen to what your math professors say. Some of that will turn up later in life when you have to learn a new technique, or a technique that's actually ancient, but it's new to you. All right, well, if I take the derivative would better be continuous. So d by dx of a times, I'm just going to factor out the e to the minus I omega t because it shows up everywhere. E to the I n1 k naught x plus r12 e to the minus I n1 k naught x. That is, let's see, every time I take the derivative of an exponential, I just get the function itself multiplied by whatever's in front of x in the exponent. So I get a e to the minus I omega t times I n1 k naught e to the I n1 k naught x minus I n1 k naught r12 e to the minus I n1 k naught x. And if I take the derivative, if I plug in x equals 0, I just get a e to the minus I omega t times I n1 k naught times 1 minus R1, 2. Now, if I took the derivative on the right side, if I took the derivative of the other expression, all right, that is going to be A T1 to I N to K naught e to the I yada 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 equals A T1 to I N to K naught e to the minus I omega T if X equals 0, because we only have to match these things at X equals 0. Now, everywhere else, it's either very clear that you're in the left medium, so you have something that involves both an incident and a reflected wave, or it's very clear that you're in the right medium, so you have something that only involves a transmitted wave. We don't have to worry about ambiguities there. It's only at the interface that we have to match these things, because that's where the ambiguities are. That's where these two things meet up. So if I equate them, if I say, hey, the derivative has to be continuous across the interface, I'm left with AE to the minus I omega T I K naught times N1 minus N1 R1 2 equals A e to the minus I omega T I K naught N2 T1 2. And I can cancel all of these things that match, because when you tweet something terrible, you get canceled. And now I have another equation that involves my unknowns R12 and T12. And I had this other equation that involves them. 1 plus R12 equals T12. Two equations, two unknowns. Thinking way back to high school algebra, that's something we can handle. We can immediately solve for R12 and T12. And before I do those steps, any questions on the process that got us here? Okay. Well, let's eliminate T12. It's also equal to that. This is the first equation. It's also equal to N1 over N2, 1 minus R12 if I take the top equation and divide both sides by N2. So now I just have one equation with one unknown. So 1 plus R12 equals N1 over N2 plus N1 over N2, minus N1 over N2, R12. If I add this term to both sides, subtract 1 from both sides, I'm left with R12 times 1 plus N1 over N2 equals N1 over N2 minus 1. R12 equals N1 over N2 minus 1 over N1 over N2 plus 1. Then I multiply top and bottom by N2, and I'm left with N1 minus N2 over N1 plus N2. Any questions? If you have no questions for me, I have a question for you. Can someone explain what on earth this has to do with the fact that the wave gets a half cycle phase shift if it reflects off a higher index medium, but not a lower index medium? Anyone? Think about what happens if N1 is, think about what you could say about this expression if N1 is less than N2.
When N1 is less than N2, the top part of that fraction becomes negative. And so the
Yep.
reflection coefficient is negative. And then when N2 is, or when N1 is greater than N2, it's positive. So it doesn't get reflected or shifted.
Oh, it gets reflected either way. What happens is that the wave's direction doesn't get flipped. The field direction doesn't get flipped. R12 is basically telling you two things. It's telling you in relative terms how strong the reflected field is. It's going to be weaker than the incident field, but how much weaker? And it's also telling you, okay, is it positive whenever the incoming wave is positive and negative whenever the incoming wave is positive? You know, do they have the same sign or do they have opposite signs? If they have opposite signs, that means that the reflected wave has effectively gone through an extra half cycle. Questions on what that means? Okay, one other thing. That explains the half cycle phase shift when we reflect off a higher index medium. But I also said that if N2 equals square root of N1, N3, then an anti-reflection coating is perfect. And we saw that in the ZMAX, sorry, not in the ZMAX, we saw that in the Python program that, you know, we played around with the refractive index of that layer. And if we made that N2 layer have a refractive index that was the square root of N1, N3, we didn't get any reflection at a specially chosen wavelength. Basically, here's what's happening. Wave is coming in. Got our first reflection. We've got our second reflection, right? If these two can perfectly cancel out, and you're thinking, wait, aren't there more reflections? Well, yes, just humor me for a moment. If these two were of the same strength, we know that this one, because it's a lambda over 4 coating, 1/4 of the wavelength inside that medium, we know that this is a half cycle, that the distance traveled is a half cycle. We know there's a half cycle here and a half cycle there. Those cancel. So we're left with these two waves that differ by a half cycle. But if they had the same amplitude, well, we'd have two reflections, two waves with equal strength, opposite direction. We'd get nothing. They'd cancel out. It would be as if they both tweeted something terrible and got canceled. So we know that that's how that works. Now, if I were to square both sides of this condition, I would get N2 squared equals N1, N3, which means N2 over N1 equals N3 over N2. This is new over old. The ratio of the new index, the one that's just coming upon, to the old index, the ratio, the index of the medium it was in at the left interface, N2 over N1, you know, the medium it's hitting divided by the medium it started in. And then this is again new over old the medium that it's hitting over the medium that it was just immediately in at the other interface. If this condition is satisfied, then these ratios are the same. Can anybody tell me why those ratios should be of interest to us in terms of the strength of a reflection? Hang on. My dog is trying to eat a lab notebook. Okay. Well, let's see. I see those ratios right here. I see that the reflection coefficient could have been written in terms of those ratios. Right? We don't have to write the reflection coefficient in terms of the index difference over the index sum. I could have just written it in terms of the ratio of the indices, or what's often called the refractive index contrast. And if I write it in terms of that ratio, that's the only thing that matters. So if N2 over N1 equals N3 over N2, then the strength of the reflection at this interface is the same as the strength of the reflection at this interface. And then we could, in principle, get perfect cancellation. Somebody must have a question. No questions? All right, I'm going to do an example now that will probably take a lot of time. We're going to be a little bit behind, and we have to stop at 6 because we have an alumni visitor coming. But it's an example that makes all of this much more visual. So let's consider our 3 materials. And let's just think about the process of all of those reflections, because one thing I've been sort of glossing over, I'm saying, hey, you know, this reflection on the left side is just as strong as the reflection on the right side. But of course, the wave that got transmitted in isn't quite as strong as the incident wave. And so what I'm really reflecting is just not a fraction of the incident wave, but a fraction of a fraction, because a fraction gets in and then a fraction reflects, and then another fraction transmits there. So it's a fraction of a fraction of a fraction. And you could say, well, how could that possibly cancel out what's here? And the answer is that all of these other reflections are also in there. So let's start writing that down. We've got our incident wave. And its amplitude, we'll just call that 1. Then we've got our transmitted wave, which has amplitude T12. We have our first reflection with amplitude R12. We don't have to worry about the reflection phase shift because it's already in there. If N2 is larger than N1, R12 is negative. So we don't have to worry about reflection phase shifts. They're already accounted for in R12. So you got this transmitted wave with amplitude T12. Now, when it gets over here, it's gone through some distance. So what gets over here is T12 e to the I N2 K naught D. That's what makes it all the way to over here. And then some of it reflects. How much of it? Well, there's a reflection coefficient R23. That's multiplying T12 e to the I N2 K naught D. then it has to travel all the way to there. Now, when it travels all the way to there, it's covered a longer distance. So now it's R23, T12, e to the 2I n2k naught d. And then some of it makes it through there. Well, how much? We have to multiply it by a transmission coefficient. T21, T12, R23, e to the 2I n2k naught d. But of course, not all of it got transmitted through that interface. Some of it got reflected here. So we got R21, R23, T12, e to the 2I n2k naught d. And I know this is all getting tedious, but what I'm trying to show you is that we could think of this process as being broken up into many steps. There's a wave that comes in, and that wave is, its amplitude is 1. There's a wave that's reflected. You figure out its amplitude from what we know of reflection at interfaces, the things we just worked out a little while ago. There's a wave that gets transmitted. We can figure out that transmission coefficient. It travels, gets a phase shift. You can figure that out. It gets reflected. Well, the reflectance, there's an amplitude for that. Then it travels again. There's another phase shift for that. Then some of it gets through. Well, there's an amplitude for that, and we combine that with everything else. Some of it gets reflected. There's an amplitude for that. Any questions? Somebody must have a question.
Professor, how many times does it keep doing that?
Infinitely. We have to write down an infinite series. You asked how many times it bounces back and forth, right?
Yeah, that answered my question. Thank you.
All right, so some of it gets through here. Well, now it's gone 1, 2, 3 passes. So RT 1, 2, R2, 1, R2, 3, e to the 3I n2k naught d. Then it gets reflected. R2, 3 squared, because it got reflected there twice. Got reflected here and there. R2, 1, T1, 2, e to the 3I n2k naught d. I'm not going to write down infinitely many terms, but I want to get it back and forth a couple times so we can see the pattern. And once we see the pattern, we can write down the infinite series. Well, then it gets to here. Picked up another phase shift, so R2, 3 squared, R2, 1, T1, 2, e to the 4I n2k naught d, because it went 1, 2, 3, 4 passes. And then some of it gets through. And that will have a T21 and a T12 and an R2, 3 squared and an R2, 1 and an e to the 4I n2k naught d. We could keep going, but what we would get is that the reflected wave is R12 plus, that's one special. There's no bouncing back and forth. The waves that bounce back and forth, well, they're all going to have a factor of T12 in there because they have to enter. They're all going to have a factor of T21. They have to leave. Right? And they're all going to have, let's see, so we're going to be summing. Every time they make a pass through there, we're going to get e to the 2 times the number of passes, e to the 2 times m times I n to k naught d. The 2 just from the fact that it's a round trip. M is the number of round trips, n2 because it's in a medium, k naught because it's a wave, d because of the distance. And for every trip it makes, it's going to have an R23 to the m, because if it makes 1 round trip, it bounces here once. If it makes 2 round trips, it bounces here again. And R21 to the m minus 1, because on the first pass, if it only makes 1 round trip through here, it doesn't have to bounce at this interface at all. If it makes 2 passes, it has to bounce at this interface once. And if it makes 3, it has to bounce at this interface twice. If it makes 4, it has to bounce at that interface 3 times. Any questions about that? Okay. Let me note a few other things before we, well, you know what, let's just do this summation. R12 plus T12, T21. This R to the m minus 1, I could write that as R21 to the m, R21 to the minus 1. So I could put that down there. Oops, that would be m equals 1 to infinity, e to the 2I n to k naught d, R23, R21, all of that raised to the m power. Any questions on how I got that? Okay, now I want to do a couple other things to simplify this. First, I want to note that R21 is minus R12. Because if I just swap these, boom, all I have to do is swap these and I am left with a minus sign, but I also go from R12 to R21. Now, T12 is equal to, well, if we look back up here, T12 is 1 plus R12. And if we just swap indices, you know, because that which we call rows by any other name would still smell as sweet. What's in the name? T21 must be 1 plus R21. That must be 1 minus R12. So move this out of the way. T12, T21 should be 1 plus R12 times 1 minus R12, which is 1 minus R12 squared. So I've just simplified some things. Which means I can rewrite this reflected field R12 minus 1 minus R12 squared over R12. Remember, the minus sign out front comes from the fact that R21 is minus R12. Then I'm going to do one other thing. Oops. I'm gonna put a -1 and start the sum at m equals 0. If we start the sum at m equals 0, well, what's anything to the power 0? Whatever R23 might be, whatever R21 might be, whatever this exponential might be, what do we get when we take the whole thing to the power 0? Don't overthink it, for the love of God.
It's 1.
1.
1. So if I added one more in m equals 0 term, I add a 1. To balance it out, I subtract a 1. Okay, now this summation, the sum from m equals 0 to infinity of x to the m is just 1 over 1 minus x. This is a very fancy x, but still, it's the same thing. So I get R12 minus 1 minus R12 squared over R12 times -1 plus, minus 1 minus R12 squared over R12, 1 over 1 minus, we'll write that as 1 plus R12, because minus R21 is plus R12. Ooh, that's a bloody god-awful mess. But now we can start simplifying some things a bit, because what else do we know? We know that this is an AR coding. D is lambda over 4n2. So 2n2 k naught d would be 2n2. K naught is 2 pi over lambda times lambda over 4n2. 2 and 2 cancels the 4, lambda cancels the lambda, n2 cancels the n2, and we're left with pi. And what's e to the I pi? It's cosine pi plus I sine pi. And what are the cosine and sine of pi? -180 degrees. What's the cosine of 180 degrees?
-1.
-1, and the sine of 180 degrees is 0. So this is just -1. So, all right, I get R12 plus 1 minus R12 squared over R12. Minus 1 minus R12 squared over R12 times 1 over 1, blah, that this is a -1. 1 minus R12 R23, which is a bloody god-awful mess still. But what if n2 equals square root of n1, n3? I said earlier that if n2 is equal to that square root, then the ratio at one interface is equal to the ratio at the other interface, which means that the reflectances must be the same. So now I get R12 plus 1 minus R12 squared over R12 minus 1 minus R12 squared over R12, 1 over 1 minus R12 squared. Hey, top and bottom here cancel. Things are starting to look promising. So I get R12 plus 1 over R12 squared minus R12 squared over R12 minus 1 over R12, because I just took this term and broke it down. Oh wait, this denominator should just be R12. Hey, these two terms cancel each other. And these two terms cancel each other. So if you look at that as algebraic gymnastics, well, you know, there's some algebraic tricks that we played in there, whatever. But what I want you to think of it as is this. We started with the physical idea that at each interface, some of the wave transmits, some of it reflects. On every pass, it acquires a phase shift. I can add up all of those effects. And under the special condition that we have an anti-reflection coding, all of this is equal to pi. So all of our phase shifts become really simple. They all become -1 because they're a half cycle. That's the physical idea. It's not e to the I, yada, yada, yada. It's round trip phase shift. If it's a half cycle, it's just a -1. And all of these things have the same amplitude because we have the same refractive index contrast. So all of these reflectances become the same as each other. If you think about it in those terms, then it makes sense that all of these things cancel. And so if N2 equals this, we get perfect anti-reflection. And so the first thing you could think is, okay, so, you know, for glass, I'm just going to make a coating with an index of 1.25, because that's roughly the square root of 1.5. What do you think the problem is?
Maybe there's not many indexes of refraction that are 1.25.
Oh, I could make something with an index of 1.25. Even I could do it, and I'm a physicist. I know just enough chemistry that I could do it with a little bit of trial and error. What do you think the problem is? Who said that this stuff is mechanically stable? Who says it's sturdy? Who says it's going to stick to glass? Who says it's going to have that refractive index across a range of wavelengths? Who says that the stuff won't have a bunch of air bubbles in it that scatter light? If all you want is a certain refractive index, even I could make it. All I do is I'd make a porous material, okay? I'd make a porous material. And somebody will say, making porous materials isn't easy. Yeah, but there are some tricks. The hard part is making a porous material that is nice and uniform, and the pores are small and they're all about the same size, so it doesn't get lumpy and it sticks to what you want it to stick to and remains strong. That's the hard part. Okay, we're going to take a break until 6 o'clock. I know it's a little bit shorter than we normally take. Then Kyle will come, and then next week we will do things with off-axis angles. So I'll see you in a few minutes. Bernardo. Bernardo. You know, you probably want a belly scratch. Come here. All right. Nice doggy. You just need attention. I know. I know. You just need attention. Bernardo, good doggy. No. You're a good doggy. Good doggy. Good doggy. Good doggy. Okay, I gotta put you down so I can do some work now. It's the work that pays for your dog food. No, you are not going to eat the lab notebook, okay? You are not going to eat the lab manual. No, you are not going to eat the lab manual. I said no. Here's your tennis ball. Oh, so I wasn't muted. Okay, yeah. So we just got a dog and, you know, he's doing what dogs do, which is explore and try to chew things and yeah. What kind of dog? He is a poodle mix. And since we're waiting for Kyle to show up, this is Bernardo. He's a poodle mix. He was a rescue. They named him Bernie, but I started calling him, the people at the shelter named him Bernie. I sort of made it more formal, Bernardo, partly because people were asking me, oh, is he named after that politician? And I'm like, no, they named him that because they found him in San Bernardino. And so they call him Bernie, and then I changed it to Bernardo. And yeah, he's finally starting to get comfortable in the house and realizing that this is his home. And I guess he thinks that means he has chewing privileges. Okay, so Kyle should be here any minute. While we're waiting for Kyle, what questions do people have on what we've done or anything with the project coming up?
What is the final project going to be like? Is it already posted?
No, it'll be posted at the end of the semester and at the end of in the last week of classes, and then you have about a week to work on it. Basically, think 2 projects. So 2 of the standard projects, and that'll be in lieu of a final exam. So one of them will probably be like the last 3 projects, something with a thin film solver, and one of them will be a Zmax project. And I'll basically say to you, okay, here's a conjecture about some kind of lens. Is it true or false? You know, I think that this lens might have this kind of performance, or hey, here's a paper where somebody built like last year's final project was something related to COVID testing. I said, hey, so people are working on a cheap COVID test that involves a sort of homebrew fluorescence kit made with off-the-shelf parts. What fraction of the light is the lens collecting? You know, the whole idea is that you take a specimen from someone, and then you have some sort of probe that glows when you shine light on it. And it also attaches to COVID RNA or COVID antibodies. And if there's COVID RNA or COVID antibodies in the specimen, then this stuff will attach to it and it will glow. And I said, okay, well, you know, in order to do that, you have to be able to detect the glow. So assuming that there's this much specimen that's located in this part of the device, what fraction of the light is going to make it onto the detector given all of these other specs? So I'm not sure what the semesters will be. I have a few ideas and we'll find out. I'll write them up in the last week. And the last day of class is just a day to take questions on the final project assignment. Let me see where Kyle is. What we'll do is we'll wait a few minutes, we'll wait about 10 minutes. And if he doesn't show up, then I would like to go over some more stuff. I'm not going to undo the delay of the project. You know, if I postponed it till Thursday, it's postponed until Thursday. But I will go over a little more stuff with off-normal incidents so that we're not too far behind and we can still get through some special topics in the last week and a half. All right, let me, Kyle, I checked with him a while ago. I should have checked in again. So I'm going to copy an invitation. Eight nine two 6276 6215. Yeah, that's what I sent him. Okay, we'll give him about 5 more minutes. Any other questions besides about the final project? Just wait a minute. Bernardo. Oh, now you want to see. One thing we haven't talked about, which I can share my screen for and start showing you, is how to do multiple layers in the Python program. So remember, we had something set up for left medium index and right medium index. And then I had this array or this list called coding layers. If I want to have more than one layer, let's make it simple again, 1.0, 1.5, and I'll make this 0.532 times 0.25, so a quarter wave. The wavelength will be 532 nanometers, and we'll just do a quarter of that wavelength. All right, let's first verify that I put everything correct. Yep. All right, yep, and this is giving anti-reflection at a wavelength of about 532, and it might look like a narrow dip, but that's because I've got the plot going from all the way out to 3 microns. If I plotted it over just say the visible range, which goes from roughly 400, maybe more like 380, 390, to people will quote different numbers, 700-ish. I've heard 760 is sometimes quoted. If I plot it over, you might be saying, how do I not know what the visible range is? Well, it's not like there's a wavelength where you can see and a wavelength where you can't. If you had a broadband light source, you'd see red and then faint red and fainter. And if you really went into, if it was really dark, everything else was really dark, and so your eyes were dark adapted, it's really hard to specify the cutoff, and different people have different cutoffs. I've met people who have unusually long wavelength cutoffs. All right, so now we've got this coding set up. What if I said, okay, let's try 2 layers. All we do is we put a comma, square brackets, and another pair of layers, another pair of parameters. So let's say 0.532 times 0.25 divided by, let's say 1.45. And the index is 1.45. So I want to put 2 of these layers in. Okay, I'll put 2 anti-reflection layers. Why not? Well, here's what happens if we put 2 anti-reflection layers. Oh, 145. Actually, let's go back to that. 145. So I accidentally put 145 for the refractive index, and I got something really, really weird. Would anybody like to take a stab at interpreting why we get so many peaks and minima when the refractive index is 145? What can we say about the wavelength inside of a medium? How does the wavelength in a medium compare with the wavelength in air?
It's smaller.
Yep. And usually it's smaller by like a factor of 1.5-ish. Well, here it's smaller by a factor of 145. So we, in essence, have a really, really thick system. We have a really, really thick system, and in a really, really thick system, for some wavelengths, we're going to have that, you know, a round trip is equal to a full cycle. And then for another wavelength, it'll be, or 2 cycles, or 100 cycles, because, you know, the wavelengths inside the system are going to be like, instead of 500 nanometers, it's going to be 500 divided by 145. So it's going to be 3 or 4 nanometers, 3 point something nanometers. But it's in this layer that's still probably about 100 nanometers across. And so you got a 3 nanometer wave traveling 100 nanometers. Well, if it's a 3 nanometer wave, it's going to go 33 1/3 wavelengths. If it was a 3 point something nanometer wave, it might go exactly 33, or 33.5, or 32.5, or 32, or 31.5. And 31.5 cycles versus 32 cycles is the difference between constructive and destructive interference. All right, but let's try now 1.45. Okay, and instead of getting destructive interference at that center wavelength, we wind up getting pretty strong constructive interference because we had 2 quarter wave layers. Anybody hazard a guess as to why? Any guesses? Well, we got 2 quarter wave layers. And yes, these 2 quarter wave layers have different indices. One of them is 1.38, the other is 1.45. But the difference between those two is quite small. 1.38 minus 1.45 is going to be 0.07. Okay. And so our reflectance is going to be, our reflection coefficient will be 1.45 minus 1.38 divided by 1.45 plus 1.38. Okay, that's going to be 0.02. So that's the amplitude. The intensity is proportional to the square of the electric field. So if the field is only 2.5%, 0.025, if the reflected field at that interface is 2.5% of whatever hit it, the reflected intensity, the actual energy per second per area that you're getting, is going to be all of that squared. So let me do that. So it's going to be minuscule. Whereas if we had an interface between air and glass, well, now we've got 1.5 minus 1 divided by 1.5 plus 1, whole thing squared. And that is 0.04. So we're getting about 4% reflectance at an air-glass interface, but we're getting like 6 times 10 to the minus 4 reflectance at the interface between these two materials. And I see that someone just joined. Andrew just joined. Kyle, is Kyle here yet? Okay, so Andrew, you just came back in. Kyle has not joined us. I'm not sure what's going on. I've sent him a message. I'm just going over some things and how to use the software right now. If he doesn't show up soon, I'm just gonna resume the lecture and we're gonna cover some stuff on reflectance at off normal angles. All right, so what we've got here is we've got 2 quarter wave layers. And yes, there's a little bit of reflectance at that interface, but not much. We could treat it as almost like 2 quarter wave layers, which would be a half wave layer. And with a half wave layer, because it's a half wavelength one way on the first pass, and a half wavelength on the other way, the round trip will be a full cycle. And yeah, we have a half cycle reflection phase shift on one side and a half cycle reflection phase shift on the other side. You might say, hey, what about that interface? The interface, it doesn't matter because there's so little light reflected there. So we wind up getting constructive interference when we put two of these half wave layers together. Now, one question we could ask, and this would be hard to do in practice, but let's do 1/8 of a cycle. So 2 1/8 wave layers. If I did 2 1/8 wave layers, then we get actually some pretty low reflectance. It's not really where I anticipated it being, but you know, you learn something new every day. I was just doing this on the fly. Interesting. Let's compare with the case where both layers have an index of 1.38, which would be the equivalent of a single layer with an index of 1.38. Why do you think there's no difference between making a single layer with an index of 1.38 and making 2 layers, each of them half as thick? Why do you think there's no difference there?
The layers half as thick, would they have also the same index?
And what does it mean when they have the same index? What's something we talked about in the first half of the class today?
Yeah, it had to do with the continuity, right?
Continuity, and what about, is there going to be any reflection at the interface?
No, not in that case.
No, because the refractive index difference will be 0. So let's just see what happens there. Okay, so the 1/8 wave layers were not quite as good. The minimum reflectance intensity was about 0.014, so 1.4%. I'm just curious about something. What if I made these refractive indices 1.17, or actually, let's do the cube root of 1.5. So 1.14, then the 2/3 root. I just want to kind of multiply by the same thing each time. One 1.31. I'm just curious what would happen. Well, it shifts to a much smaller wavelength, but it also goes much lower. Once you go beyond one layer, a lot of things become harder to predict by rules that you might do by hand. Let's just take a look and see what that would look like. Instead of going down to 0.38, let's go down to 0.3. Let's go down to 0.2. Okay, so right around 0.4, we shift it to a shorter wavelength. We shift the dip to a shorter wavelength. We make the dip much lower. We also make it narrower. Any questions, either about the particular examples I've chosen or about how to use the code to work with more than one layer? Part of your assignment on the next project is to put in more than one layer. You have to look at a patent for an anti-reflection coating on polycarbonate and go into Google Scholar, find this patent, and then look in the patent and see, well, what did they specify for the thicknesses and refractive indices of the different layers? And I was hoping Kyle would be here because his senior project was on reading patents of thin films and trying to actually simulate them with the parameters that were in the patents and see if the simulations would predict the kind of performance that they claimed in the patents. And for the most part, they did. But the biggest thing he learned was that patents are designed to disclose as little as possible while still meeting the requirements of the law. Can anybody tell me why? Anybody tell me the rationale? Have we talked about patents before this semester?
I don't think so.
Okay, so who knows what the rationale is? Well, who knows what a patent actually means and does, what it enables you to do as a patent holder if you have one?
I believe it means something along the lines of having some sort of intellectual property that you
Okay.
can market for a period of time. And that's just it. It prevents other people from using that intellectual property or physical, that idea, and marketing it.
Yes and no. A patent means that nobody else can do what you have patented. Nobody else can make that. However, you are required to disclose things in your patent. Normally, the government is not in the business. Well, governments do all sorts of terrible things. A government is actually trying to do something sensible, should not be in the business of telling people not to make things, telling people not to sell things, telling people not to make a new invention. But they make an exception for patents because you have to disclose. You see, there are plenty of things that aren't patented and people sell them and make a profit off of them. Those are trade secrets. Coca-Cola, nobody knows the exact formula for Coca-Cola. All right, Coca-Cola is not patented. A patent says basically this. All right, you come up with an idea, great. You want to have exclusive use of that idea? Great. Okay, well, there's two ways you can make exclusive use of the idea. One is to not tell anyone else. Okay, you want to do that, do that. Two, you can get the government to go after people who use your idea. And the government says, we'll do that, but we'll only do it for a limited time. And we'll only do it if, and it's usually like, I think 18 or 20 years, I can never remember the exact number. We'll only do it for a limited time. And we will only do it if you disclose what you did. So the whole idea is that nobody else gets to do what you've done, but everybody gets to find out how it works so that they can try to improve on it. And until they improve on it, you've got the hopefully best thing out there. Now, once they improve on it, well, then, maybe people will still buy your thing because it's around, it's reliable, it works. They don't care about the improvements, or they don't want to spend the money that the improvements would cost. So it's a way of trying to spur progress. It says, okay, you come up with an idea. We will help you make a profit on it by protecting you from competitors. But we will insist that you disclose key things so that other people can innovate. So it protects your incentive to innovate, and it gives other people information for their own innovations. This is all the theory behind it. Now, of course, people who actually work with patents, people who work with anything will tell you that they never work exactly as the theory would predict. I'm telling you the rationale. Whether it lives up to that rationale is a whole other matter. Sometimes it does, sometimes it doesn't. What times are those sometimes? Ask someone who works in that area. but that's the idea. And so you're going to go into a patent and look and just see, well, first of all, what is it like to read a patent? What do people normally say in patents? And then you'll find out what are the layer thicknesses and refractive indices that they used. And the way that you code up something with more than one layer is by simply going into coding layers. And for each layer in brackets, you have two numbers, the layer thickness and a refractive index. And then for the next one, the layer thickness and a refractive index. Any questions? Okay, let's talk about off axis. So far, we've been talking about waves hitting things at normal incidence, but of course, waves don't hit things all the time at normal incidence. Sometimes they hit at off normal. Sometimes they hit it off normal. And what we want to try to figure out is what would the condition for constructive or destructive interference be if they hit at off normal incidence? And it is very tempting. By the way, before we actually even get to what's tempting, how would you figure out theta 2? I told you N1, N2, and N3, and I told you theta 1. How would you figure out theta 2 inside this layer?
We would use Snell's law.
Yep, Snell's law still works. A common question I get from people is, do I just use Snell's law here? Yep, Snell's law still works. Snell's law is not one of those things that nature turns off when somebody notices that the wave is, well, a wave. Okay, so a common assumption people make is, oh, well, the extra distance must be this hypotenuse plus this hypotenuse, right? Wrong. I mean, these two hypotenuses are part of the extra distance, but you also have to take into account this, okay? Basically, let me do that in a different color. That blue part here is extra distance covered by your first reflection. And these are extra distance covered by your second reflection. So let's do that geometry, right? That was, let me try to do this diagram a little bit neater. We've got a wave coming in here, and if I do that so that angle of incidence equals angle of reflection, it will look like that. And then I'm going to do something that looks like this, and I'm going to say that, oops, I'm going to do this in a different color. Actually, I'm going to do that at an exact different. obviously different angle. And then I will have this be up there. And I think if I've done it correctly, that all of these are now parallel. All of these things are at realistic angles. So here's theta 1. All right, and I'm going to call this delta, and I'm going to call this L and L. And so what we need to figure out is 2L minus delta. Except really it's 2L 2N2L minus N1 delta. Because the difference in distance, the difference in cycles is going to be 2L over lambda over N1 minus delta, N2, minus delta over lambda over N1, which is 2L N2 minus N1 delta, whole thing over lambda. Any question on that idea? Okay, so we've got this distance y here. And we could say that this is theta 2. Tan theta 2 is equal to y over 2 divided by the coating thickness d. All right. Oops. Tan theta 2 is y over 2d. And we could also say that L is the hypotenuse of a right triangle. L cosine theta 2 is equal to d. So we've got this angle theta 2 here. If we take its tangent, we can relate it to y and d. And if we take its cosine, we can relate L and d. This is sine theta 2 over cosine theta 2. I could then say that y over 2d times d is equal to y over 2d times L, y over 2d times d is equal to tan theta 2 times L cosine theta 2. You know what? I'm making this way harder than it needs to be. L cosine theta 2 equals d. L sine theta 2 equals y over 2. Let's just go with that. I'm sorry that I made it harder than it needs to be. Okay. Now we've got this delta here. And let's see, this is theta 1. So this is 90 minus theta 1. And then because it's all in the right triangle, that's theta 1. So y sine theta 1 equals, oops, delta. All right, any questions on that geometry so far? Okay, extra cycles in medium 1 is going to be y sine theta 1. I know what I needed. Okay. Y, we need to eliminate y. Sorry. We eliminate y by saying that y is equal to 2d tan theta 2. Which means that y sine theta 1 is equal to delta is equal to 2d tan theta 2 sine theta 1. Then n1 delta would be n1 sine theta 1 times 2d tan theta 2. Okay, so we've got n1 sine theta 1. This is something that shows up in Snell's law. And we've got something that involves medium 2. We might have a chance of making all of this work. Meanwhile, L is d over cosine theta 2. And 2n2 L is 2n2d over cosine theta 2. And we need the difference between those two. We need 2n2L minus n1 delta all over lambda. So we need 2n2d over lambda cosine theta 2 minus n1 sine theta 1 times 2d tan theta 2 over lambda. Now I know this looks like a hopeless mess, but notice that I've just written this phase difference entirely in terms of the layer thickness. All right, so that's encouraging. We figured that anything involving thin film should depend on the layer thickness. I got rid of this Y and L. Everything is now in terms of the layer thickness. Also, N1 sine theta 1, I could just turn that into N2 sine theta 2. And so now I've got that the difference in cycles is equal to, let's see here, N2d over lambda. I'm pulling out everything that shows up in both terms. I got an N2, a D, an N2, a D. I get a 2, I get a lambda in the denominator. And tan theta 2, well, that's sine theta 2 over cosine theta 2. All right. And so what I'm left with is 2n2d over cosine theta over lambda cosine theta 2, 1 minus sine squared theta 2. Because I've got a sine theta 2 here and a sine theta 2 there. How do I simplify that?
It's just cosine squared.
Yep. Yep. So I've got 2d cosine squared theta 2 over cosine theta 2 over lambda over n2. And I'm writing that as divided by lambda over n2 because we're dividing by the wavelength in that layer. So I'm left with 2d cosine theta 2 over lambda over n2. Now that does not look at all obvious. That doesn't look like anything that you would have just stared at and guessed and said, oh yeah, that's got to be the answer. But it turns out that it actually does have there is a way for us to interpret it. Okay. Given that this is the difference in the number of cycles, well, let's see here. The difference in the number of cycles. I've got something that's inversely proportional to lambda, and it has cosine theta 2. Now, cosine theta 2 would show up in the x component of a vector. Okay, so if this is my x direction, the x component of a vector in this medium would be proportional to cosine theta 2. I had some vector pointing in the same direction that the wave is traveling, its x component would have cosine theta 2. What vector might that be? A vector that's in the same direction as the wave and whose magnitude is inversely proportional to the wavelength.
Oh.
Yep. Kx would be 2 pi n2 over lambda cosine theta 2. So the difference in cycles here would be up to this factor of pi, 1 over pi times kx times d. Or let's make that a 2 pi in the denominator. You'll see why. Now let's make that a 2d up top. Then the difference in cycles is kx times the round trip distance. So the way we do any problem that involves a wave hitting a multi-layer film or a thin film, if we want to figure out from the round trip what kind of interference we get, well, we still say, okay, at this surface, is it high or low? All right, we still ask that question. And likewise, at this interface, we still ask, are we reflecting off of high or low? And so we might have reflection phase shifts, we might not, it all depends. And then our round trip phase shift is equal to 2d times kx over 2 pi, or 2d times cosine theta 2 or divided by lambda over n2. Let's do an example and then we'll call it a day. So let's say that we've got, yeah, I can draw it better. We've got air, we've got oil, and we've got glass. And this is a high index oil, N2 is 1.6. And this glass is N3 equals 1.5, N1 equals 1. And we send in the light at an angle of 45 degrees. right? And what we want to know is what wavelengths are strongly reflected. Oh, and D is equal to 500 nanometers. Okay. Does the first reflection get a phase shift? Does the reflection here get a phase shift?
Yep.
1/2 cycle phase shift. Does this reflection get a 1/2 cycle phase shift?
No, it doesn't.
Now, in order to figure out the phase shift due to the round trip, we have to figure out theta2 via n1, or just 1 times the sine of 45 degrees equals 1.6 sine of theta2. And so sine of theta2 would be, sine of 45 degrees is 0.707 over 1.6. And I'm not going to run it through a calculator right now, but theta2 is equal to 26.2 degrees. A lot of people, for some reason, when they do a problem like this, they just want to assume that theta2 must be 45 degrees. And then I have to take off a whole bunch of points. Theta2 is not 45 degrees. You have to use Snell's law. So cosine theta2 is 0.897. All right, so we get that for constructive interference, we're going to have, let's see here, 2D cosine theta2 times whole thing times n2 times 2d times cosine theta2 divided by lambda minus 1/2 cycle, because this is the round trip phase shift. This is the first reflection. What should that be equal to for constructive interference, for strong reflection?
M.
Yep, it should be an integer. So 2n2d cosine theta2 equals m plus 1/2. Oh, all this should be divided by lambda. So lambda is 2n2d cosine theta2 over m plus 1/2. And then we could just start plugging in numbers. 1.6, 500 nanometers, 0.897. My monitor, okay, there. So if we plug in all those numbers, we get 2870 nanometers, m equals 0. 956 nanometers, m equals 1. 574 nanometers, m equals 2. And 410 nanometers, m equals 3. Other than the fact that, I didn't run the calculator in front of you, does anybody have any questions on this? Okay, so on Tuesday, I'm going to say a little bit more about reflection, about off-axis, and then we're going to talk about some effects with polarization, and then we'll talk about some interesting devices that involve thin films and show up in lasers. Have a good weekend.